So this slide summarizes the threats to validity of pre-experimental designs, and it's a useful one-page summary where the pluses on this chart indicate the design is strong on that particular threat versus the minuses, which suggests a weakness of that design, and a question mark suggests that it depends. I want to move to quasi-experimental design, and this design definitely has much more potential in terms of attributing effects to our program. So what is quasi-experimental design? It is design in which there are multiple measures, so multiple O's, or else multiple groups, and sometimes both. Generally, but not always, quasi-experimental design has a comparison group or comparison groups, but does not randomize participants to the two groups. So this is not a randomized design. However, it has many features that can eliminate threats to validity. It is frequently used in evaluation because randomization can be difficult, or there could be ethical or legal prohibitions against randomization. It may be difficult to find an exact control group, or sometimes there are just not enough resources to conduct a randomized study. So let's start with a common quasi-experimental design, the pretest-posttest non-equivalent comparison group design. So a few things about the wording here. Pretest, post-test, you should already be familiar with. You know that there is going to be an O before the intervention and an O after. The word non-equivalent simply means that the groups have not been selected through randomization. They are convenience comparisons in a sense. So this may be one neighborhood of the city and this may be a similar neighborhood, or this could be a state and this could be a similar state or states. And again, this is indicated by the dashed line here that shows that these two groups are non-randomized. So here is the pretest-post-test comparison group design in which we administer a pretest, do a program, and then check the post-test outcome. You'll note that this is very similar to some of the previous designs, except the difference is that in our comparison group, or in a group that is not receiving the X, there's no X here, we are also doing a pretest and a post-test to see what would have happened in that group without the program. One other note before I move on, which is that we, in program evaluation, use the word comparison group to indicate groups that may or may not be randomly selected. When we use the word control group, we are speaking about a randomly selected group. So we should really be discussing comparison groups when we talk about quasi-random designs. So what are the threats to validity in a pretest post-test comparison group design? Well, if you think about this design does partly control for history threat. So if the groups are similar and subject to similar external forces, then what would happen is this comparison group, the change in this comparison group, would reflect the work of other threats or other rival hypotheses besides our program. Since they didn't get the program, any change from this O to this O would be picking up the history threat, also the maturation threat potentially, also the testing threat. So if there was some learning, if there was some learning between this O and this O, it would be picked up again in the change between these two observations. In a way, you can think of this comparison group as acting as a sponge for all the threats, or several of the threats that might be rival hypotheses to our program. So again, history threat could be controlled, maturation, testing, and if the instruments changed across the groups, you would be picking that up as well in the comparison group level. So what this does introduce is, however, a selection threat, which again, if you recall, is the threat that these groups are actually different to begin with. They're fundamentally different, and a group that is stronger or weaker on a particular variable that you care about may perform better even without the program. We control selection threat best by randomizing, but if we can't do that in these quasi-random designs, we want to ensure that the groups are as similar as possible. However, I think one very important point is that even if groups are statistically very similar, mean ages and social backgrounds and so on, they may still be different in ways that we can't measure. A great example is volunteers. So if one group or intervention group actually volunteered to be in the program and the comparison group looks exactly the same demographically as the intervention group but didn't volunteer to be in the program, I think you can all imagine that the volunteers would be different. They would be more motivated. They may have more motivation and gumption for success in this program. And so just be aware that demographic comparisons of the two groups are not sufficient in terms of making sure that there's no selection threat. The other threat that there may be is regression. If the groups were selected on the basis of low or high scores, which I didn't say that they were in this case, but if that is the case, then regression may be a threat. A variation on the pretest-posttest comparison group design is something called the double pretest design. And if you look at this, you now have two observations before the intervention. So two O's, the intervention, and then the O. And again, the same thing happens minus the intervention in the second group, the comparison group. And again, groups could be neighborhoods, they could be schools, they could be states, and so on. So here we have these two waves of data collection where we're observing, let's say, the healthy eating behaviors through a survey. And we have two observations, and the question is why? Well, one important benefit of this design is it allows us to map the trends before the intervention. In a way, it helps us address the concern about selection. So what are we doing? By doing two observations of healthy eating in our intervention group and two observations of healthy eating in our comparison group, even before the program, we can see which way this group is going. Is there already an underlying trend in which there's knowledge increase? And if so, is that increase greater in our group than in the control comparison group, or is it the other way around? It gives us a little bit of assurance about what was happening before we got there, and the way to understand what was happening is to measure the trend, which requires several observations. A very useful and underused design, I would say, is the single or interrupted time series design. And this design, again, should make sense to you now by looking at the notation. We have several measures, surveys, or several waves of data that come in before the intervention, and then again several surveys that come in after the intervention. You need at least two before and two after, ideally even more, to make it a time series. So what happens here? So an example might be that you're trying to increase immunization rates through a health education program. That's your X. And so what do? You measure immunization coverage each year for 3 years before your program. That's the O's. Then you give your program, and then you measure immunization coverage in the 3 years after the program. And this is a very powerful design. Let me show you some ways that it's been used. This is data on hairdryer electrocutions from Rogers et al. And what it plots is deaths due to hair dryers that were dropped in the bathtub or other water between 1980 and 2007. And what you can see here is they have time series data. So what you don't see is the little points here, but they're all joined in a line. They have multiple observations between 1980 and around 1987 or so. And what they're doing in this study is they're extending that line and saying, well, mathematically, if this kept going, this is what we would have seen. So you can see there was already a downward trend in these electrocutions. But what they are able to show, at least mathematically, is that once legislation came in that had hairdryer immersion protection requirements, so ways to make the hairdryer turn off when it hits water, this is the trend that would have happened without. And so what they're really showing graphically is the big difference between the expected and the actual trends. So showing how time series data are used. In a sense, this is sort of multiple time series. This will be the expectation without. They're creating an artificial comparison group, the counterfactual, and then the group that actually was protected. And the reason for this is because these hairdryer protection requirements were national. Okay, so single time series, threats to validity. It's a very similar design to the pretest-posttest design, but it reduces the maturation, testing, and regression threats. Why? Well, you're picking up the maturation before the program's ever there. So if you see a significant deviation from the line, from the slope, then you know something's going on that's above and beyond maturation. Testing is also eliminated because you can see, or mitigated anyway, because you can see how much the tests matter. If in fact you are doing repeat surveys, you can see how much knowledge gain, for instance, there was between the first and the second wave. And similarly with regression threat. There's no selection threat here per se because there's no comparison group. History threat is partially controlled, and again, and let's go back to the notation. If the history threat, if some event occurred over here between this first and the second O, you would have picked it up already before your program ever got started by seeing the change in these two O's. The reason I say it depends on the timing is if the history threat occurred right in the middle of this time period, right around the same time of your intervention, there would be no way in this design to pick up the attribution of your particular program versus what the other program may have contributed. So that is one problem. But if the history thread happens at any other time, it would be picked up presumably by these observations. Attrition is in a sense a threat because people can change from the first year to the second year to the third year. People can leave the city or new people can come in. And so that is a threat, and you should probably compare the composition of the population in all of your measurements throughout time. Instrumentation threat is really only present if there was a change in the instrument around the time of the program itself. Again, similar to the history threat. And this is a page that tells us a little bit about the different patterns one can see in single time series observations. Here is an intervention. There's a number of observations here and an intervention here showing a change in level. So whatever we were measuring here went up dramatically. Here you can see a change in slope, so there isn't this dramatic rise, but over time beyond the intervention you see an increase. Here there was a big rise and then a continued rise, suggesting the intervention is having some sort of a knock-on effect that's lasting over time. This is a fairly common scenario D, where it actually takes longer than you think to have the effect. There is a delayed change in the level or a delayed change in slope. Scenario F is one we all want to avoid, which is that the change is really only temporary, and over time you do see a decline to normal. And that's, by the way, another strength of single time series or any time series designs, is that it allows you to see how long your effect is sustained. A few other points on this slide. Scenario H shows that there was already a rise in the performance of this outcome variable before your intervention came in, so that would suggest there actually isn't a program effect. And finally, option I here shows that this outcome varies dramatically, perhaps seasonally or cyclically, and so depending on when your program came in, you might think you've reduced the outcome or increased the outcome, but really what you're seeing from these trend data is that there's a cyclical effect. There's no program effect at all. All right, so let's move to the multiple time series design, which is very similar to the single time series except with a comparison group. So multiple time series is lots of observations and two or more groups. And so what is this? Again, we could be collecting immunization data for 3 years, but this time in counties where there will be an intervention and in counties where there will not be an intervention, and comparing their trends over time. Let's see what this could look like. First, though, the controls here are much stronger for history threat because the external event might cause a jump in the outcome for both groups, provided they are similar. And again, we're always concerned that the groups be similar, otherwise we have selection threat. So I really like this example which was an example of trying to reduce newborn mortality in several counties in the United States between 1964 and 1984 over a 20-year time period. And the intervention is called RICP, Reducing Infant Mortality in Rural America. It's the Rural Infant Care Program. And what you can see here is that the intervention counties are black dots and comparison counties are the clear dots. And what do we see here? Well, first of all, our program, by the way, is this line here around 1978. And what you can see here is that, first of all, there is clearly a downward trend in newborn mortality over time, as you can see by the line sloping downwards long before the intervention ever hit. And in fact, the downward slope is present in both the intervention and the comparison counties. But what's also very interesting here is that once the intervention was implemented, you do see the distance between the comparison and the intervention groups closing, so that the intervention counties which were performing poorly, by the way, the higher the number of deaths, obviously the worse performing the county is. Now the number of deaths is falling. There's a fairly dramatic drop from maybe this line to this line. And you see the gap closing here. This observation doesn't look persuasive, but certainly over here they're closing the gap between the intervention and the comparison. And just graphically, you can look at this and say, you know, that this looks like the program may have been effective. And of course, you would do some statistical analysis to back up that intuition. A similar example, another interesting example is data on fatal and non-fatal traffic injuries in France. And this is between 1999 and 2010. And so what do we see here? There's a lot of very interesting things. This study was assessing the effect of announcement of traffic cameras to try to capture speeding drivers and the actual introduction of the traffic cameras and what really made a difference. So before we go there, let's look and see what's going on here with the trends. And just right away, you can see there's a lot of ups and downs in these traffic death trends. The solid lines are non-fatal injuries, and the dashed lines are fatal injuries or deaths. So both of these go up and down depending on the season, and it looks like there's some seasonal variation throughout the year in France, probably to do with holidays and driving amount and so on. And these are per 100,000 registered vehicles. Okay, so there's the seasonal fluctuation. Now, in July of 2002, President Chirac at the time made the announcement that they would be instituting traffic cameras. And what's happening here is you can see that there is a downward, sort of if you just draw a straight line across these, that there is a downward trend right starting after the announcement that could be perceived. And when the cameras were actually introduced, there is a smaller change both in the peaks and the troughs in terms of the traffic deaths and injuries. So this is actually very interesting, suggesting that just the threat of these cameras may have made a difference. And what you can see here is a statistical analysis that shows that the announcement by Chirac was associated with a reduction in traffic fatalities per 100,000 registered vehicles, and similarly that the intervention itself was associated with a reduction. So no matter which model you use, and they use many different models, they really found the same thing. So this is a very interesting study using multiple, this is single time series. All right, so to summarize quasi-experimental design, this is a design that is frequently used in evaluation research and can be an excellent design in terms of internal validity. Each of the various options I showed you has some pros and cons, and not least of which are just feasibility of getting these data. Obviously, multiple time series and single time series relies on administrative data or data that will be readily available from programs that don't require laborious surveys every time. And typically that's where we see time series data. But it is a great option if you can do multiple time series or single time series in order to evaluate your program. And again, this is a one-page summary of the pros and cons of the various designs.